2000 says, answer the following questions about the element selenium. Selenium. Hang on, let's find old selenium on here. Selenium. There's selenium. Just selenium. Oh, whoa. Sorry, didn't mean to do that. That's lame. Sorry.
My favorite element is... I don't have one yet.
That's okay. You're young.
Oxygen.
All right. A. Samples of natural selenium contain 6 stable isotopes. In terms of atomic structure, explain what these isotopes have in common and how they differ. Okay, so let's first of all make sure we understand what the heck is an isotope.
Different amount of neutrons.
Different number of neutrons is what I'm hearing.
But, oh yeah, this one's easy.
It is super easy. So, again, we want you to explain what they have in common. So, same number of
Protons.
same protons. And does it say that it's neutral? Doesn't say if it's neutral. It says natural. But if it's neutral, what can we say about the electrons?
Same number of electrons.
Same.
Electrons.
Yep.
Yeah.
And what do they have that differ? Neutrons.
Exceptional answer then, isn't it? But
That is
But you can't
amazing.
say electrons because we don't know that for sure.
I would say
Then they're
if
four
neutral,
electrons.
again, they're assuming that it's neutral. I think it's safe to assume that it's neutral because it didn't say selenium ion. Same number of protons, same number of electrons, if neutral,
Oh my goodness.
different number of neutrons. That's what isotopes are.
I
All
don't
right.
even need to mention 4 electrons.
Yeah, ignore that.
Letter B.
Guys.
Write the complete electron configuration, and it gave you an example, 1s2, 2s2, etc. for selenium in its ground state. What does ground state mean?
No charge.
Uh-oh. What does ground state
How
mean?
it is found on the periodic table.
It's neutral.
What does ground state mean?
The amount of protons is equal to the.
What does
when it's-
ground state mean?
When it's just normal.
What does ground
Is it
state?
not just SE?
Normal.
No, it's
When it's found, when it's at,
It's placement on the table.
What is ground state? Anyone?
No one knows. I don't
Oh,
think.
is it with
What
the
is
lowest
ground
electron
state?
configuration that it
The lowest, you're warmer,
lowest energy state of quantum mechanical system.
the lowest amount of energy, so there are no excited electrons. So,
So no charge.
Never mind.
oh God. So selenium is element number 34. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, yes we do, 10, and 4p, 1, 2, 3, 4. Just that easy.
I'm confused. Why did we have to struggle with ground so much?
Because you guys didn't know it, obviously.
How would it
There's just
change
like-
if it wasn't, if it didn't?
If it were to be excited, a possible configuration would be this.
Oh my Greg, that's literally what I said.
You said nothing of the sort. This would be excited.
Is that what it would ask? Would like the AP people be like, indicate the number of unpaired electrons in the excited atom?
No, that would be really rough.
Okay, then what would they say?
You would be given some multiple choice options and possibly say which one is excited.
It would ask excited?
Definitely not the
That's
person
kinda
taking
cool.
the test.
So
Okay.
first of all, you have to make sure you have how many electrons represented. Oof.
34.
34, good. So if it gave you an electron configuration for something other than selenium, you can toss that out, which also happens. And then if it says that it's excited, then it's going to be in a higher energy level
But it could
before it
this
fills
one.
up the other ones. Go ahead, what?
So it could have this one as multiple choice for excited, but it would be wrong because it's in the ground state.
Correct.
Okay, that makes
Very
sense.
good.
Thank you.
All right, C.
No, there's a second part.
Oh, sorry. Indicate the number of unpaired electrons in the ground state. Ah, yes, very good, very good.
So when you draw that,
Oh, wait, so here I
There are
will.
2 unpaired. Wait.
So we go 1, 2, 3, then we double up. Where some chuckleheads out there
like me.
would do this because they don't know nothing.
And then
Wait,
This is very
can
bad.
you like walk through how you do that one? Because I still don't understand.
The bottom one or
chucklehead,
this
but
one?
that one?
That one?
Yeah. Like,
According to eyeball principle, we drop 1 electron into each orbital. Since the
Okay.
P's have 3, drop 1 in before we go and double up.
okay.
Yeah, don't double up until you're forced to.
Like,
Go ahead. So the one that I
This
just,
would be the first one. This would be the second.
So
This would
what's
be
your
the
reasoning?
third.
There you
This
go.
would be the
There
fourth,
are
and then
two
go back
unpaired
for
electrons
that. Oh no.
no. So there's 3 orbitals
of
for the P's. So you're gonna, each orbital maximum can hold 2 electrons.
Yeah. I knew that one.
Okay.
Right?
So I don't know what you're asking.
Oh, never. I tried to do them all and then explain it.
Got it.
So your explanation. What's the principle again? I'll be.
You don't have to know the name.
Okay.
It's Allball and Hun that are the
So-
2 guys that
There are 2 unpaired electrons because of Aubon and Hun.
there are, and I would just say there are 2 unpaired electrons, and I would show this. and
you
be
don't
done.
have to say because.
Yeah, because did it say?
It says. Well, it says.
Oh, explain your reasoning. So I would say that you would place 1 electron into each orbital before going and doubling up.
this. Well,
Hang on.
There, it
Light.
starts at electrons. Sorry, it starts at electrons.
Good. Yep.
yeah.
Yep.
Yeah.
All right. Everybody good with, what is that? B? Feeling like a
What if
villain.
I wasn't okay?
Yeah.
Well,
one second.
we'd
Let me
still
put my
move
fingers.
on.
We're done.
All right, C. In terms of atomic structure, explain why the first ionization energy of selenium is less than that of bromine. So let's go to bromine. Let's see where selenium and bromine are at.
Bromine is
So, bromine's right next door. So we're looking at these 2 right here. So it says that selenium has a lower first ionization energy than bromine, which I really like. So what can we say about this?
Bromine has a stronger force of attraction because it has more protons than selenium, causing the distance to get smaller, therefore increasing the force of attraction. So it has more attraction on the bromine, which means that
I love it. Hopefully you heard that. So the bromine has a smaller radius because it has more protons than selenium, 1 more,
and then
while
same
the
number
core
four.
electrons are the same. Not a bad idea to incorporate core electrons when you talk about protons.
Are they the same?
The core electrons are the same for both selenium and bromine. However, bromine has 1 more electron than selenium.
Yes.
It has 1 more proton. The core electrons are the same. So we're not going to worry about valence when we talk about that, because as we add more and more protons, those electrons get tighter, closer.
And that's why it shrinks.
You got her.
Oh, you
Eric?
did it.
There's hope for you, my man. I like it. All right, double I. So the first ionization energy of selenium is greater than that of tellurium, element number 52. So right above it. Okay, so we'll zap that. So we're now comparing these 2 critters. So selenium has a higher first ionization energy than tellurium. Why?
Tellurium has more core electrons than selenium, so it has another orbital filled, therefore increasing the radius.
Good. So we want to talk about tellurium is in a higher energy level, which means that it has more orbitals with electrons occupying it. Selenium is a smaller radius, therefore the force of attraction is greater, therefore the ionization energy should be greater. And again, good news, this is being recorded.
Nice.
Okay.
So
Fun,
it has
fun,
more
fun.
orbitals.
More
I
orbitals
can
with
say it out
electrons.
loud.
Yeah. You don't get to lead the cheer tonight. Okay.
Yeah, she's gonna go.
Yeah, I gotta go play in a old
Oh,
haunted
that's
church with
right.
Emma.
You did say that. Oh boy. Everybody good with C? Need more time? Okay. Letter D. Selenium reacts with fluorine to form SeF4. Draw the complete Lewis electron dot structure for SeF4. Whenever you see electron dot, please show all the electrons or represent all the electrons. Okay. So go ahead and draw that first. Then we'll talk.
Let's see, 6.
There you go.
Alice, I can't do this in my
34.
head.
Did she pull a calculator out?
Yes, she did.
Oh no, it's one of these ones.
And don't forget about formal charges.
I love.
I wrote a lot more than
Oh yeah, I just drawn the other thing. I don't really remember what else asked. Sketch the molecular structure. Okay, so 1, 2, 3, 4, 5. That's a.
You want to see mine so you can get the exceptional answer again?
Oh, I put mine down. You put yours up.
Oh no.
I put mine down too, Mr. Craig.
Atta girl. All right. Molecular structure, which hasn't been asked for a while, but it's not a bad idea to know how to draw a molecular structure. The molecular structure only shows the atoms and the connections associated with it. So it would look like this. I hear banging going on.
Oh, because that's just the.
I was drawing the actual.
And more accurately, what is the shape of the SeF4? Seesaw. So it's a seesaw within a trigonal bipyramidal. So we have, and this is the more accurate way to draw a molecular structure. Hang on here. That one would be accepted. Yeah, I did. So we have, let's see, we've got fluorine along the plane. We have another fluorine along the plane. Then we have a fluorine coming out of the plane. We have a fluorine behind the plane. And we have a lone pair on the plane. You don't have to draw it like that. If you drew the molecular like the one above, so when you see this like bulky triangle that's thick, that means it's protruding above the page. The dash means it's behind the page. Solid lines means it lies on the page. So when you look at this trigonal when you look at this trigonal bipyramidal shape, let's go with the camera here. That'd be better. Back on it. So when you see this trigonal bipyramidal shape, that we could orient it so we have these three on the same plane. This one comes out of the plane. This one is behind the plane. So that's why I have the 3 lines that are solid represented here. This one's the chunky arrow. This one is behind up here. I know the great job for that. It was asking for what?
So let's say, now this wouldn't happen, but if
Okay.
chlorine was a double bond, you would do the 2 lines.
So double bonds, triple bonds, it still would dictate how the shape would be on a plane or whatever.
Okay,
So like
but-
if let's do another one. Give me another shape. Like which one do you want to look at? Just give me a shape.
Tetrahedral. I like.
So tetrahedral. So methane is a great example of a tetrahedral. So what that means is that if we were to draw that out, that would quote unquote be the Lewis structure. You would have, let me go a little thinner here. So that means you'd have a hydrogen here, and I believe you'd have another one here. This guy would be chunky. And then we'd have another one behind. Yeah, so it protrudes out. Now, I have not seen molecular structures for a while. I mean, I'm talking well over 10 years. So it's not a bad idea to know about it.
So, like with a double bond.
Okay.
Like, with
So-
this guy, would you do the
So
sectional line
we'll
here?
pretend that hydrogen has a double bond. This is going to hurt to do this, but it would look like that.
Okay. Yeah.
Now, the bad news is it's really difficult to show it like that. So you'd want to put your double bond on the plane.
I just dumped water.
That girl. Okay.
Wet.
All right. So if you drew your molecular like this, I'm okay. You want to play like a pro, do it like this.
I'm not a pro.
Nope.
I will be going better safe than.
Yeah. Yeah.
Okay.
I don't see myself doing that.
Yeah, don't be surprised.
Thanks.
Thank you. I'm glad I'm meeting your expectations. But I got the other 2 questions down.
Alice, that's your thing.
Oh, you don't want to do
Yeah,
that.
Alice, you can draw like that.
No, it
You are
ain't.
the star of AP Chem.
All right, let's see. What else? Indicate whether the molecule is polar or non-polar.
I don't turn my
It is polar because it's asymmetric.
Excellent. So it's a polar molecule. The justification is it has a asymmetric geometry
With a lone pair.
with the lone pair within the seesaw structure.
Oh.
Do we need to do the SP
You need to do
stuff?
all of that?
I'm so happy.
It would be nice. So
I will do all
Emma
of
just
it.
asked, do we have to write all that? It's not a bad idea.
What if I say like seesaw and it's not seesaw? Then my entire thing's wrong.
Yeah.
Yeah.
Well, so make sure you give me the correct structure.
So is that enough?
I didn't ask for hybridization. So no. So this bottom part right here, the polar asymmetrical, you got to tell me why it's asymmetrical.
Because of the lone pair.
There's a lone pair within a seesaw shape. Yep.
Let's go, Greg.
All right.
Why is this one within a seesaw shape instead of like within a trigonal?
Well, if you want to say has a lone pair within a trigonal bipyramidal forming a seesaw, that too would be acceptable. But the seesaw technically has a lone pair. What's your name? Are you sitting on the lucky stool?
No.
Oh.
No, no, no.
The lucky
Over
stool is
there.
over there.
No
I
one
know.
wants the naked stool.
All right. Any questions about 2000? Good. Let's look at 1996.
That's not on the schedule.
It is now.
Is it the bonding question?
I don't know.
It is.
That's a good question. All right, 1996. This will be our last question for the day.
Chill out, Greg.
But then
What?
we go on a walk there?
November 9th. November 9th.
Oh yeah, we can totally go on a walk after this.
Possibly, yeah.
Yay! Thank you, Mr. Craig.
Bonding, I think, if you're doing this all separately.
Yes, it is called the bonding question. The NIMSY bonding thing. I
It's
just love
November
that.
9th. If you go to the proposed schedule.
Ooh.
Alice memorized it. Her
November
eidetic
9th?
memory over
No,
here.
it is right there.
Thank you. I know.
Craig, how long was that stool in your shower?
A long time, I guess.
It was about a month or so, and
That's a
then it
long
started getting
time.
moldy. So I'm like, I gotta get this out of here.
What if it like rocks out underneath my body?
And then
Like,
she goes,
what if it just cracks under me? The weight of me. Like, if I just sit on it and
I don't think
the
anything-
mold
Are
would
you guys talking about the
Patch of
school
blood.
that was in his shower?
Yes.
Yeah.
That's what we're talking about.
That's disgusting.
It's not like I. All right, 1996. Explain. Hang on. Shh. Explain each of the following in terms of electronic structure. Whoa. And or bonding of the compounds involved. A, at ordinary conditions, HF with a normal boiling point of 20 degrees Celsius
no one cares.
is a
Whoa. That's low.
I care. I'm sorry.
is a liquid, whereas HCl, normal boiling point, is negative 114 degrees Celsius, is a gas.
How can I have a wait?
Why in the world would one have such a higher boiling point than the other?
One's not a gas or a liquid.
Oh, HF. Yeah, Alice, you're right. It's a hydrogen bond for HF. And HCl is not a hydrogen bond. Oh, just kidding.
What?
Maybe not. Oh, yeah, that is an intermolecular.
It is.
Huh.
What?
Yay.
If you skip the video about intermolecular
didn't.
forces, you better watch it this weekend because you're going to be asked about things like this.
What day?
We skipped the video?
That's a very good question.
It's
Did
like
you skip a
London.
video?
It's like the London dispersion
Oh.
You know what? A London
forces.
dispersion force and
Yeah.
hydrogen bonding.
Evidently, he don't know.
I've heard of it. I've heard of it.
Uh-huh.
Dipole, ionic, metallic.
You don't get it?
I definitely skipped it.
I forget.
Was that early or?
Yes,
It
sir.
was later. Like, it was one of the last. I think it was the second to the last.
Beginning of this week?
Oh my
I'll
God.
watch that. I swear.
False.
Dude. Can you
All right.
stop exposing me, please?
So, why does HF have a higher boiling point than HCl?
HF is a hydrogen bond and it's stronger than the than HCl.
Which has what kind of bonding?
Oh, let's help. Dipole.
Dipole. So the HF has hydrogen bonding. Make sure you know the conditions for hydrogen bonding. I'll give you a hint. NOF. Not CNOF, NOF. And this has dipole.
What's the conditions for example?
You.
Dipole is
Really,
when
Craig?
it's polar. And, yeah.
Okay.
And then
So they're both polar.
Yeah, but.
The HCl has dipole, intermolecular forces. Intra is the type between atoms. Which is stronger? The intra or inter?
intra.
Good. Because back in the day, this was and again, this is a sidebar, this is not asked. There was a statement that said, true or false, your best friend tells you that when water boils, it breaks down into hydrogen molecules and oxygen molecules. Again, when it boils. And then explain why it is true or why it is false. Go ahead, Levi.
Okay. So it's all it's doing is changing
Up.
state. Really?
True or false? Answer the question.
Oh, sorry, dude. It's what my friend is saying is false.
Okay.
Yeah.
Why?
Because it's only changing state of matter. It's not boiling it does not break the bonds.
It does not. Because also what uncharacteristic event would occur if you were boiling water in your kitchen around fire and you produce hydrogen gas and oxygen gas? You would explode every time.
Yay.
You put on the test last time an explosion as one of the multiple choice answers, and I almost put it just because I even circled it and put, should I put this?
So we indicated that the HF has hydrogen bonding. So what?
Hydrogen bonding takes more like force to break the bond, so you need a higher boiling point.
Okay. So I'm hearing that hydrogen bonding when the molar masses are relatively similar. Now, again, 35, 36 versus 20, it's not too bad. It's almost double, but we're not talking like hundreds of grams different. We will talk about what happens, why chlorine is a gas. Here, let me put it up here. Dang it, come here. In other words, why chlorine is a gas. Dang it. Chlorine's a gas, bromine's a liquid, and iodine is a solid. All three of these, Cl2, Br2, and I2, have what type of intermolecular forces?
No, because they're not
Together, so
molar,
it's
so
not
it's
London.
London
They have
dispersion,
all
'cause it's
have London
non-polar.
dispersion forces.
Oh,
They
that's
all
okay.
have London dispersion forces. So why the heck is chlorine a gas, bromine a liquid, and iodine a solid? It all goes back to Coulombic attractions. So if we come back and go away there, whatever that thing is, if we look at this, what has dramatically increased?
The positive, and so the distance becomes smaller and the force of attraction becomes greater.
Oh, really?
Wait, maybe not. I don't know.
So you're telling me, hang on here.
Because it gets more positive.
So you're telling me that the iodine is so much smaller than the chlorine?
Oh, no, because it has more core electrons. And so the valence is.
What else?
bigger.
Let's take a look at this versus this
Oh,
versus this.
Molar mass. You did.
The mass, which goes back to, dang it. So it goes back to the equation, wait, that as you increase the number of protons, what happens to, we don't care about the distance this time, what happens to the force? It increases. That is how you explain why chlorine is a liquid. Chlorine's a gas, bromine's a liquid, and iodine's a solid. They all have dispersion forces, but as you increase the number of protons, the force gets greater. Now, you could argue and say, well, the distance is getting bigger as well. But in this case, it's more about the protons. Proteins.
Steak.
Because here's what you can't argue. You can't say, well, it shouldn't be chlorine's a gas, bromine's a liquid, and iodine's a solid. Well, sorry, fella, it is. So we got to have something to explain that trait. So it's all about the protons. And as you get more massive, think about the sun. As you get more massive, what happens to your gravitational attraction for neighbors? It gets larger and stronger. So you can think about that as well. That actually leans toward physics when we talk about that equation. Okay, so we're increasing the number of protons. Don't be surprised if you see something like that.
That question's going to be on the test.
Oh, I don't know.
Explain this.
You might have to, yeah. All right, so going back to our question. So it's all about the intermolecular forces, and that the hydrogen bonding in this case is much stronger. We can't argue with the information given to us. One thing I don't want you to do is say, well, this question's wrong. It's wrong because hydrochloric acid has a larger mass. It's wrong. No, it says this is the boiling point. We have to account for why it is. And the hydrogen fluoride has stronger hydrogen bonding than the dipole-dipole. It's wrong. But it ain't.
Is that what all I have to put for the explanation?
It's not bad.
Okay.
All right, letter B.
Not bad, it's good magic.
Molecules of ASF3 are polar, whereas ASF5 are not.
Do I even have to draw this out?
I would highly recommend you draw this out. Since I don't know where in the world it says it in the instructions. Okay.
Oh.
So, not a bad idea. It's all good. It's all good. No. Nah, it's all good. Nah, it's good.
I'm just aggravating him a little bit up here today.
No.
Okay.
Oh my God. Calm 5, Bubby.
I accidentally said an E instead of an F. That would change it.
All took my periodic table today. I don't even know. I can't see it.
There's not even an E
Five,
on the periodic
7.
table.
There's an E. Nope, there isn't. You're right.
7.
There's an ES or an EU.
Forte.
5 plus
Dee-dee.
7 times 5.
Dee-dee.
40.
Dee-dee.
Am I?
Always go with formal charges. Dee-dee-dee-dee. Probably not.
That's that was really mean.
Oh wait, there's a 5 there. My bad. It's not a lone B.
I did it.
I could do it correctly.
All right. So the question asks, molecules of ASF3 are polar, whereas ASF5 are not. Why? And you can't just leave it as a Lewis dot structure and walk away.
So we can't say that it's
Trigonal
symmetry?
bipyramidal. There we go.
Oh, we can't
So
say
this
that.
one has symmetrical geometry. In other words, there's no, actually, let's say all external atoms are the same. All external, and I'm abbreviating. And there are no lone pairs on central atom. Central. What's the matter? Ryan, are you back there playing on your phone, preparing to fail for the next test? Dang, son. Whereas the ASF3 is asymmetrical
and has a lone pair on the central atom.
with a lone pair of electrons. It's good. It's not a bad idea. On central atom.
I don't even know how to spell this.
Get it close. This is not English class.
I messed it up.
It's one
Okay.
S, 2 M's, right?
Sure.
Well, that doesn't help me.
I put an H in there.
An H.
You're like, I don't know if I wrote that subconsciously and like,
And no bonds.
I'm not gonna go back and change it.
What?
This whole thing being recorded.
What?
This whole class.
Yeah, I can edit. Don't worry.
Oh, don't edit Ryan falling asleep.
Ryan. All right. Any questions on this one because I'm about to erase? Aim high. It's all right. We need ditch diggers.
Oh my God. That's not nice.
Yeah, it's true. We do. All right. Letter C. The NO bonds, plural, and NO2 -1 ion are equal in length, whereas they are unequal in H, NO2. You have never seen this before. Wah, wah. But we talked about it.
So we guess.
No, you do not guess.
Educated.
You would draw it out. Good night in the morning.
Is that a negative charge on it?
That is a negative charge on the NO2,
So my calculator said there was.
whereas,
Yes.
oh my God. Emma Marie.
Is that a witch smell? I was like,
No, her middle name is not Marie though.
It's good enough.
Emma Marie kind of sounds correct.
Yeah.
I don't know.
So 18. I'm guessing the other one's 18 as well. Would I be correct?
I haven't done that calculation.
Yes,
Isn't
it
that
is.
wackadoo?
It is.
It is.
It's so wackadoo.
They did that on purpose, didn't they?
Yes, they did. Huh? That's a 5. Sorry. Yeah, it's a bad 5, but it's a 5. There. All right. So oxygen.
Oh. No.
And so we want 3, 1.
Sure. Wait. Oh.
So there is your -1. Here we have a
Oh, that's what I did wrong.
think. Let's go with that.
Wait.
I like that.
That is wrong. That's not 18 electrons.
Mr. Craig, am I an idiot or shouldn't that be 19 electrons?
You're wrong.
But there's 5 in the
What?
nitrogen and
Yeah.
then 2 from the hydrogen. That's 7.
Whoa. Where are you getting 2 hydrogens?
I'm looking at 1 hydrogen. Oh,
Okay, 1 hydrogen's
sorry,
good.
my bad. My bad.
Well, I did that.
Welcome.
Oh, I did this.
Oh, that's all right. You and Levi are like 2. Never mind.
Craig, how do you know to put the hydrogen on the other side of the oxygen?
It doesn't matter.
So can I put it below the nitrogen?
Yeah. Also, I like what you just asked.
Where'd you get the negative?
Hey, Craig, can you get rid of the -1 charge?
Yeah.
Oh, my bad. Sorry. Thank you. Yeah, it is bad. It is. Habit bad. Over here. Okay. And actually, let me draw it this way too.
So are we supposed to know that you put the hydrogen on the oxygen and not the nitrogen?
That is a fact.
Fine. But no. Is hydrogen like being with oxygen?
Yes. Yeah. In other words, according to formal charges, nitrogen wants how many shared pairs?
3.
3. And how many lone pairs? 1. So if you put the hydrogen on the nitrogen, there's 4 shared pairs, no lone pair. Okay. All right. So let's get to the oomph of this question. Okay. So looking at these 2 shapes, which represent the same thing, it's a resonant structure. In other words, the double bond could be on the left side or it could be on the right side. And the reality is it's on both and it keeps switching. Okay. So the average length, this is where a question like this comes into play. If we have a double bond, is a double bond longer or shorter than a single bond? Shorter, very good. So it's closer. So it goes, here, let me go. We'll just draw it here. So, and I'm going to, not to scale, but single bond, double bond, triple bond. Okay. Terrible representation, but it does get the point across. Okay. So we have to have some lengths associated with a double bond and a single bond. So if I keep having the double and single switching sides, we can say that the average length is between a single and a double, which would be 1 plus 2 is divided by 2 is 1.5. So if you want to make it simplistic, we would say the lengths of these bonds are 1.5 long. And you're probably saying to yourself, 1.5 of what? Great question. But if you come over here, all I've done is rotated the molecule. In other words, if you take your hand and make the, what is that, a peace sign? What is this sign here?
That's rock on.
Rock on, a rock on sign, and you turn your hand. That's all I've done. Take the rock on and twist it 180 degrees. So again, which one is longer, the single or the double? The single. So does the single bond, if you have your hand in the rock on, does that single and double change places? No, because we just rotated it. So in this case here, that is a single bond, which has a length of 1, and the double bond, we'll just say it's half that. So when we are asked the question over here, the NO bonds and NO2 are equal in length, your answer would be because you have a resonant structure. Whereas the double bond and the single bond are not a resonant structure in this case, since we have the hydrogen attached. We actually have an acid here, which we haven't talked about yet.
We have to have the resonance in our.
I would talk about the resonance because it literally does switch between the oxygens, and the average equals the same length.
We can't just say that because the HNO2 has a sharing.
No, we don't want to talk about sharing. It's talking about the length of the bond. So a single bond is going to stay as a single bond in this structure, where a double bond is going to stay as a double bond. So these lengths are not equal. And that they're not asking you to determine how long or how short. It just says, why are they unequal? That's all we care about. So resonance, they should be the same. Go ahead.
Is that one too then? Like the bond length because it has the extra single to bond
Are we,
hydrogen?
wait a minute, which one are you talking about?
The hydrogen one.
Oh, we don't care about this one. Is that what you mean?
Yeah.
We're not care.
So
All we
the
care about is
hydrogen-
the bond between the nitrogen and right here. This is the bonds that we're concerned about. The NO bonds.
Okay.
All right, last question. It's a humdinger. For sulfur, the fluorides SF2, SF4, SF6 are known to exist, whereas for oxygen, only OF2 is known to exist. What the hootie hey?
Oxygen's in the second energy level, so it can only have, never mind, 8 electrons.
God, you were so close.
Dude, that is
Sulfur includes d orbital.
Okay? So what I'm hearing, Levi Hush, is what I'm hearing is that the only shape that we can have with oxygen with a correct formal charge is that OF2 exists. And that deals with the CNOF principle, that we cannot violate the octet rule for oxygen, and oxygen doesn't want to have 4 bonded fluorines based on formal charge. However, if we were to draw these out, the formal charges would be wonderful. But the problem is talking about the SF6. How can sulfur have 6 fluorines?
Because it's in a higher energy level. Oh, it doesn't have the d orbital. Oh,
It has access to d orbitals.
Yeah.
That's all you got to say. So SF6 has access to d orbitals, where all of these shapes are good and the formal charges will work. However, oxygen only has access to the s and p orbitals, or the octet rule, and the formal charge.
I'll add the S&P.
Thank you.
So SF6 has access to the d orbitals.
Yep. Actually, sulfur has access to the d orbitals,
And
which allows all of these shapes to be formed. Is not enough. Talk about the oxygen as well.
Well, you say oxygen does not. What do you say about that?
You
It only has
oxygen
access to
only has
S&P
access to the s and p orbitals, which means you can't violate the octet rule, and the formal charge on oxygen wants 2 shared, 2 lone. It is true.
Well, sulfur wants to have the double too, though, doesn't it?
Sulfur wants to have a double.
No, because it's gonna be essential, so it has access to the deal, so it can take a lot more.
It'll actually, since the fluorines are on the outside,
And they only want to
they're all going to be single bonded with 3 lone pairs there.